working on cosmology, experimental cosmology, but today he's going to talk about cosmic voids.
All right, thank you very much. Thanks for having me. So when we look out at the large-scale distribution of matter in the universe, our eyes are naturally drawn to the overdensities, the galaxies, clusters, filaments, walls, all the stuff that makes up the cosmic web. And when we build instruments to extract cosmological information from the cosmic web, we naturally target the overdensities. We do galaxy surveys, or cluster counts, or H1 tomography. But there's more information in the cosmic web than just in the overdensities. There are also the underdensities, the cosmic voids. These voids were first discovered in some of the earliest redshift surveys. The same surveys that first identified some of the largest structures in the universe, like walls and filaments, also identified these large empty regions that we call voids. And as we go out to ever larger, higher redshifts and mapping out larger volumes of the universe, we see that voids are a generic feature of the cosmic web. And there's certainly plenty of voids, just like there are plenty of clusters and walls and filaments. These voids must carry with them cosmological information, because they mirror the growth of voids in our universe mirrors the growth of structure in the universe. As the initial density perturbations in the early universe grow and matter collapses onto sheets and filaments and eventually clusters, they evacuate these regions and leave behind these empty holes. So by studying the properties of these holes, say their size distributions or shape distributions or their interior structures, we can learn about dark energy, dark matter, the growth of structure, the large-scale cosmological questions. Now, there's a few advantages to studying voids than in studying overdensities. One, they're abundant. Most of the universe, by volume, is inside of a void. Secondly, they exist at a variety of size scales. We'll see that voids are anywhere from 5 to 50 or even 80 megaparsec across. And all voids at all scales carry with them cosmological information, either in their distributions or in their interior structures. So we're able to probe cosmology at a variety of size scales simultaneously with the same survey. And we're going to see that voids are actually relatively easy to identify. We can apply topological algorithms, I'll describe these in more detail later, to identify voids. They're actually easier to identify than bound structures like halos or clusters. And primarily, the biggest advantage voids have is that they're relatively free from systematics. If you're trying to extract cosmological information from, say, a cluster of galaxies, it's pretty much hopeless because of all the complex baryonic astrophysics inside of that cluster completely washes out any cosmological information. So if you want to use baryons and collapsed overdense baryonic structures, you have to go to very large scales, such as the baryon acoustic oscillation field. And since you have to go to such very large scales, this fundamentally limits your statistics. But voids, the motions of galaxies and dark matter inside of voids are still in the quasi-linear regime. They're very close to the initial density perturbations. This means that there's still a few systematics left in voids, but they're very easy to model. You can write down analytical expressions for the velocity flows of matter inside of voids, and they are subdominant to the cosmological signal in void. So even though a void is relatively empty and the signal inside of a void is relatively weak, the cosmological signal inside of a void is weak, if you're able to extract that signal, you don't have to do a lot of work to model out the systematic effects. You have direct access to the cosmological information in the void. Over the past few years, there's been an explosion in interest of voids. mostly because over the past few years we finally have high quality, large volume redshift surveys where we can map out and extract hundreds of voids from a single survey. And now that we have hundreds of voids to play with, we can think of things to do with cosmology. We can look at their size and ellipticity distributions, the average shape and the average size of voids as a function of redshift tells us about cosmology. I'll talk about the Alcock-Paczynski test and the integrated Sachs-Wolf effect in more detail later. You can look at the interior structure of voids, the velocity profiles, and these are excellent laboratories for dark energy and FFR gravity and fifth forces. Because inside of a void, fifth forces are completely unscreened, and so you get the largest deviations from lambda CDM general relativity inside of voids. I'll talk about anti-lensing later. That's a really interesting topic. And you can even do with voids, if you're sick of cosmology, you can even do astrophysics. You can compare galaxies inside of voids to galaxies inside of clusters, and compare and contrast populations and colors and metallicity to look at the effects of the environment on the formation history of galaxies. And you can even look at magnetic fields, and I'll talk about that one more later. But if we want to do science with voids, we have to be able to find voids in the matter distribution of the universe. And it's easy enough to pick out the voids by eye. They're all the empty spots. But we need to do this algorithmically. And historically, there's been a progression of ideas. The first void finding algorithms were based on very thin slices of redshift surveys, whereas those thinly sliced, you can consider the survey as two-dimensional. And you simply pixelize your galaxy distribution, and for each pixel you ask, do I have a galaxy or do I not have a galaxy? If the pixel doesn't have a galaxy, it's called a void pixel, and you collect together adjacent void pixels into groups, and that gives you some sense of the voids. It gives you some sense of the volume distribution of voids. It gives you some sense of the total fraction of the universe, or your slice of the universe that you're observing that exists in a void. But obviously there are shortcomings to this approach. A more sophisticated technique relies on building spherical underdensities. This is analogous to building spherical overdensities to identify bound structures in the universe. Well, here you just grow spheres until they're big enough that they contain a certain density threshold, and that's your underdense region of the universe. And you can allow multiple spheres to merge together, to overlap, so you get some sense of the shape of the void. And these algorithms also give you member galaxies inside the void. So you can distinguish populations of galaxies that are inside underdense void regions of the universe, and those that are part of bound structures like the filaments and clusters. This algorithm has a couple of weaknesses. One is it requires a lot of tunable parameters. If you go from a dark matter distribution to a galaxy distribution, then you need to change the parameters for growing the spheres and allowing spheres to merge, and the calculated mean distance between particles in order to get a sensible void population. So every time you change the sample, you need to retune your parameters in order to get a void population out. And secondly, this algorithm doesn't give you a very good sense of the true shape of a void. You can get the contents, but since you're assuming voids are always spherical or a bunch of spheres lumped together, you don't get the detailed boundary along the filament, which we're going to see is very important for determining the true shape of the void. So the approach we're going to take is a purely topological approach to identifying voids. It's a combination of Voronoi tessellations and what's called the Watershed algorithm. The Voronoi tessellation is just a phase where we take a set of tracers. These tracers could be dark matter in a simulation, it could be galaxies in a redshift survey, it doesn't matter. It's just a set of tracers. The Voronoi tessellation places a polyhedron around each particle, where the face of the polyhedron sits at the midpoint between a particle and its nearest neighbor. So I completely cover the entire volume with these sets of polyhedra called Voronoi cells. Each of these cells maps the local volume of each particle. And it is the only topologically correct definition of the local volume of that particle. There is no other definition that makes topological sense. Now that I have the local volume of the particle, I just invert it, and now I have the local density of each particle. So the Voronoi tessellation transforms a set of tracers into a map of the local density. And you can imagine this map with the local density has hills and valleys and ridge lines and basins. It looks like a topographic map. And you can imagine pouring water onto this map. And the water will naturally collect into basins. We identify these basins, or recognize them, as the cores of voids. And you can imagine on this map that there are ridgelines and a spine of mountains. And as we pour water onto this spine of mountains, occasionally a water droplet will hit this spine and go one direction, and another water droplet right next to it will hit the same spine and go another direction. Ridgelines are places that split the flow of water. Well, we recognize the ridgelines as the walls and filaments and sheets in our density distribution. They are the places where are the boundaries of voids. So as we fill this topographical map up with water, the water naturally collects into basins, which are the cores of voids, and the water identifies these ridgelines, which are the boundaries of voids. And as we fill up with water, we just collect Voronoi cells, adjacent ones, neighboring ones. We group them together to form a void until it reaches a ridgeline, a place that divides the flow of water, and that's where we can separate one void from another. So this is a purely topological approach. There are no tunable parameters in this algorithm. You have no choice. This is the Voronoi tessellation for this set of tracers. You don't get any other tessellation. This is the watershed division of that Voronoi tessellation. You don't get any other choices. So this allows us to move from dark matter, high-resolution dark matter simulations, all the way to sparsely sampled galaxy surveys as tracers of the dark matter distribution, and it allows us to apply the same algorithm without having to tune any parameters, without having to worry about how the effects of our parameters impact our voids. This is the watershed-defined void population for these tracers. This watershed algorithm allows us, in addition, allows us to uncover the full hierarchy of voids. Just like there's hierarchy of structure in the universe, there's clusters and substructures and sub-substructures within bound objects in the universe. There are voids and subvoids and sub-subvoids and on and on and on. There's hierarchy of voids in the universe. As we pour water into this topographical map, there might be a very low-lying ridge line between two voids. So initially we identify two independent voids, but as we fill up with water, it covers up this ridge line, and we can merge them. So at a larger scale, we identify one large void that contains multiple subvoids. You can see here from this, this is a slice from a dark matter simulation. And the dark lines here are 15 megaparsec voids identified by these very high density ridge lines. And embedded in them in these colored blobs are 6 megaparsec voids. So this just shows you two layers of this void tree that you naturally get. So this allows us to get the full hierarchy of voids. So we can use all the void information there to do cosmological analysis. We're not stuck to just one scale. Yeah?
Two questions, comments. First, we're giving every galaxy equal weight.
I'll talk about that.
Second is, you were defining voids by the density field, and also could define them by regarding the potential of the source of that density field.
Yes, absolutely. There are multiple ways to define voids. Probably, you can also define voids by, say, the velocity flows. You can look at the way that tracers are moving. Voids are defined by outflows of particles. This is hard in say, a redshift survey. This is a very easy algorithm to implement in a redshift survey.
Right.
Or you could try reconstructing the potential.
Seems that would be hard to do, actually. You just see the weight now by the velocity.
Yeah, I mean, you could build it, but you still need some way of deciding, is my patch of volume part of the void or not part of the void?
Well, sure, but then the algorithm would be saying it's just that the services do not define the density field, right?
Yeah.
Sorry, so voids of a given size are defined by, there's no smoothing going on here. So if you have a 10 megaparsec void, its boundary would be a very sharp, much smaller scale.
Yes, yes.
Is that
In
wrong?
fact, that's key to what really makes this watershed algorithm work for voids, is that the boundaries between voids are at a much smaller scale than the voids themselves. They're very sharp and very thin compared to the voids themselves. That makes it much easier for this watershed algorithm to find a very well-defined boundary of voids.
So when you call it's when you say 6 megaparsec voids, you just fill it with water until the average void size is 6 megaparsecs, and then
I fill it with water, and there's a ridgeline. And I fill it with water, and eventually there may be two 6 megaparsec voids that are right next to each other. Say this one and this one. But there's a relatively low density ridge between them. So identify that as a ridgeline, the place that splits the flow of water. That as I fill up, that ridgeline gets covered up. So there's still two adjacent voids because there's still a high density region between them. There's still a wall or a filament or a sheet between them. But as I fill it with water, I see that I can merge them. There are some boundaries that are so high that I could fill up the whole universe with water and I would never be able to go over that deep.
right. I'm just saying that if and you have a paren, right? So 6 is a number you just pick, right? It's a paren.
For this, this is just an illustration of I have a whole set of voids covering a variety of size scales from 6. This is from Boz et al. 2012. To something like 30 or 40 megaparsec structures. This is just picking out the 15 megaparsec ones and the 6 megaparsec ones, just for illustration. But I have a whole bunch in between.
So how do you decide that you're at 6 megaparsecs? So you have to add some amount of water, and you're at 6 and your structure is now with 6 megaparsec voids, right? And then you have to have some decision making. Say that, okay, this is how much water I need for 6 megaparsecs.
No, any set of ridge lines, as I'm pouring in this imaginary water, any set of ridge lines that bounds a 6 megaparsec region is a 6 megaparsec void. This is the boundary of the void. It's contained within a larger void. But if I fill up with water, all I notice as I start filling with water, I notice that there's a void here that eventually gets subsumed, that eventually becomes a member of a larger void. But I didn't have to make any cuts or decisions. I simply noted that as I was filling up with water. It's not like I stopped filling up with water and look around for all my voids. I just note any ridge lines at any stage in the filling up with water algorithm. At any stage, any place that gets separated off by a set of ridge lines gets counted as a void. It's added to the list.
There is a sort of, I mean, each of these cells are like some random anisotropic shape. There is a sort of arbitrariness on exactly what you count as the scale of. Pick one of those cells.
You mean one of the Voronoi cells?
Yeah.
There is a little bit, I mean, yeah, because there's a lot of fluctuations in these shapes. So to start off with, in this particular implementation, we just drop one bit of water in, and you can imagine just shaking it, and you see where this water goes, and it gives you a sense of grouping some nearby Voronoi cells into like a core of a seed, a somewhat larger core. And then from there, you begin the watershed algorithm actually grouping together these zones. That's just to take care of a little bit of the Poisson fluctuations, to smoothen those out a little bit. So we're going to apply this algorithm to data. In particular, we're going to take the SDSS, Galaxy Redshift Survey, a spectroscopic survey of a few 100,000 galaxies out to a redshift 0.5 or so. And we need to do a couple things to the data, massage it a little to work with our algorithm. The first is that we're going to make cuts in redshift and magnitude to create what are called volume-limited samples. So here's absolute magnitude versus redshift of all the galaxies in the main sample. And we're going to take 4 redshift slices and cut these off. What these volume-limited samples do for you is give you a relatively uniform density within that redshift slice. And this means, going back to your question, is that we can weight each of these galaxies relatively evenly. We don't have to weight by magnitude. There may be some biases due to color. Blue galaxies, more tightly clustered. For now, we're going to ignore that. That's a subtle modification that we still need to investigate. But we don't need to weight by magnitude or luminosity. We can just assume every galaxy is representing the same chunk of dark matter. So we're going to create 4 samples out of the main sample and 2 out of the luminous red galaxies. We don't need to do this for our algorithm to work. We can run this on a full magnitude limited sample, but this just makes further analysis a lot easier. It allows us to combine voids from one end of a redshift slice with another without having to do any reweighting. It allows us to assume that we have roughly constant number density around the surface of the void. It just makes life easier for void analysis, not necessarily void finding. But the biggest thing we have to deal with is the mass. The survey doesn't cover the entire sky, and there's holes inside the survey. So to deal with this, we don't want our voids extending out into regions where we don't observe it, and don't have any information. So we pixelize the mass, and we stream a set of Mach particles, very high density Mach particles, along the survey boundary and around any internal holes. And we give these Mach particles essentially infinite density. So what this means is that as a watershed algorithm is operating and Voronoi cells are getting collected together to form voids, if a void happens to butt up against the survey edge, it sees an infinitely high wall and it prevents the void from extending out past the survey. However, we have to be careful with voids near the edge because we don't know their true size and we don't know their true shape. So if we're trying to do any measurement of, say, the ellipticity distribution or the size distribution, then any voids that are truncated near the mask edge are going to bias some results. But if you're just interested in, say, galaxy populations inside of voids or the volume fraction, the universe inside voids, then you don't care if it's an edge void or not. So we're going to make 2 catalogs, one called all voids, which includes voids near the edge or near any internal boundaries, and another catalog called central voids that we make sure are not affected by any of the boundary particles. Where in this central sample, we believe we have a fair sampling of the size and ellipticities of the voids. So here's what a typical void looks like in the SDSS. It's very very much not spherical. Voids tend to be elliptical. You can see the complex structure of all these little facets, of all these little Voronoi cells that have been grouped together. And the void is bounded by these red dots, which are the galaxies, are bounded by these walls and filaments and structures that constrain its growth. So I'd like to show you a quick little movie showing the distribution of voids in the SDSS. Here the voids are represented as pretty low resolution, so they just look like little arrowheads. And these are 8 to 10 megaparsec voids. And you can see that they're tightly clustered at lower redshift. They tend to peter out at higher redshift. This is because at higher redshift we have lower sampling density, we run out of galaxies. And so we simply don't see the smaller 8 to 10 megaparsec voids at higher redshift, just because there aren't enough galaxies there to capture all the filaments and walls. But we definitely see them at lower redshift. And within a particular sample, they're pretty evenly distributed with the number density of the voids is pretty much constant as a function of redshift. We can take our voids that we found in SDSS and play some interesting games. Just looking at basic statistics, one of the most interesting things we found is a almost qualitatively universal one-dimensional radial profile for the voids. Here's density as a function of radius for 10 to 15 megaparsec voids, 20 to 25, 50 to 55, 90 to 95. Each of these I've taken 20, 100, tens of voids in each particular sample and added them, stacked them on top of each other to get a smooth profile. And here, the different colored lines come from different samples, so a low redshift sample and a higher redshift sample. The solid line are all voids, including ones near the edge, and the dotted lines are central voids. And you see this qualitatively universal shape where you have a very underdense core, a very steep wall. This is defined by the boundary that you have the walls and sheets and filaments at the edge of the void, so you get a very steep wall. And slightly overdense bump called the compensation region. This is where matter is flowed out of the void and ran into structure, and so it slows down, so you get a slightly overdense bump, and then asymptoting out to the mean density. And we see this at a variety of size scales, all the way from 10 to 90 megaparsec. And since these samples are probing different redshifts, this is qualitatively universal across redshift. We see it at low redshift, 0.05. We see it at 0.2, moving around 0.4. We see this qualitatively universal shape of all voids. So that's just one example of the kind of games we played with voids in our paper, and we collected all of this into a publicly available catalog, cosmicvoids.net, which isn't just voids in the SDSS, it's also all our derived data products. So our number distributions, those one-dimensional profiles that I showed you, all the things you need to completely reconstruct our paper are publicly available online. We're also turning this into a hub for void-based research, where people can come and gain access to the catalog, where we can work with them, do their analysis on real data. We're also making available mock catalogs, catalogs from later releases of the SDSS galaxy surveys, from high-resolution simulations, a variety of void catalogs, so you can really dig into your analysis and see if a particular science target is feasible with SDSS or a later survey. So we're reaching out to a lot of these groups working on different void things, giving them access to the data, working with them, and I'd like to highlight just a few, some of these research projects that people are working on. The first thing you can do and this is something we're working on ourselves, is just ask, is lambda CDM compatible with the population of voids that we see in the universe? It's a fair question. So here in the red line, there's the void cumulative number distribution, number function. So number of voids greater than a particular size. And this is actually from CMAS. This is from data release 9 of the SDSS. Here, red line are all voids, even ones near the edges. Dotted line are the central voids. And in blue is from 100 mock catalogs from Mineradol 2012. These are the same mock catalogs used in the BOSS analysis, for their analysis. So it's the same mock catalogs using a halo occupation distribution and the same mask applied to the data as close as you can get to the actual data. And in green, just a sanity check is just placing random particles with a Poisson distribution. What kind of void population do you get from that? Looks nothing like the void population in real life because galaxies are not randomly distributed in our universe. There's pretty much agreement. There maybe is hints of a slightly different slope, but it's not very large. And certainly there's some uncertainties in the halo occupation distribution prescription, in the simulations used to generate the dark matter, and there's no marginalization over cosmological parameters. This just fixes one set of parameters. So there's a lot of wiggle room in the mocks that is probably greater than the spread that's shown here. But even then, without that, there's still broad agreement. So we really see no conflict between lambda CDM and the void population in the data.
Just to get a unit in terms of gigaparsec or gigaparsec cube, as you say, your selection function is a weighted changing function, so you potentially see the smaller unit easier when they're nearby. So is this like a distance weighted average number, or do you compensate for the one in this kind of?
So this, the CMAS, this particular sample is from redshift 0.5 to 0.6. So you're actually covering a couple gigaparsec in volume. And again, CMAS is actually designed to be a volume limited sample. They selectively take redshifts of galaxies in order to get relatively uniform density. So this is a slice of the universe, 0.5 to 0.6, with relatively uniform number density. Redshift 0.5 to 0.6 for this sample. And the mean spacing of galaxies in this is around 15 megaparsec. All right, so one particle per however many cubic megaparsec. But the mean spacing between galaxies in the sample is 15 megaparsec, and it's uniform throughout the sample, and you're covering a couple gigaparsec with the sample.
So these radii are based on the volume, right? And what is the typical density in these voids? Is it the mean, or is it half the mean? Typical density?
It's around 0.2. 0.2, the mean number density of particles. So a void is no more dense than around 20% galaxy density. Another interesting thing you can do with voids is correlate void positions on the sky with fluctuations in the CMB. And you get a tiny effect called the integrated Sachs-Wolf effect, where a photon coming into a void, or comes into a void, and in the meantime, the evolution of the universe happens, dark energy affects the shape of the potential of the void, and so the photon coming in sees a slightly different potential than the photon coming out. And for voids, this tends to give you a slight cooling of the CMB photons. Now, of course, this is an incredibly tiny effect, but if you're to stack up many, many voids together, along with their associated spots on the CMB, you might see this signal. And the signal can tell you the strength of this signal, and the temperature profile can tell you a lot about cosmology. Well, I was part of the Planck team that did this, and if you stack 200, 600, or 900 voids in our catalog, this is the added CMB, stacked CMB image that you get. And here's the temperature, radial temperature profile. These dotted lines represent 1 and 2 and 3 sigma significance. So you start off with actually a relatively hot spot. And we're not entirely sure where this hot spot is coming from. It might be an artifact of our void finding algorithm, which tends to place a galaxy near the center of the void, just the way the tessellation, the watershed algorithm works. So there's a slightly overdense bump in the center of every void, but then there's definitely a cold region surrounding that, and then again, a hot ring past that, which can easily be understood in terms of that compensation region, the slightly overdense bump around every void could lead to a slightly hotter region in the CMB, but we're able to detect this ISW effect to around 2, 2.5 sigma by adding up a few hundred voids. Another thing you can do is galaxy lensing. Just like clusters and dense structures can lens galaxies, background galaxies, turn galaxies into arcs and rings, you can have anti-lensing around voids. But instead of arcs and rings, you get spokes. You tend to turn galaxies into spokes pointing inwards to the middle of the void. Now again, this is a very small effect, but the advantage of voids is that they're relatively large projected on the sky. Remember, these are 20, 40 megaparsec structures. So when you're trying to calculate the shear profile, you have to do a line integral, and you end up having a very long line integral all the way around the void. And this compensates for the relatively weak signal. And when you stack up many, many voids together and try to get a total anti-shear profile, with Peter Melchior at Ohio State, we're able to do this. And we see a dip in the shear profile at about the radius of the voids in this particular set. And we're writing this paper up now where we can detect, using gravitational deflection of light, be able to probe the inner profile of voids, which is potentially incredibly powerful because this allows us to access the density profile inside of voids without relying on tracers inside the void itself. So we can look at the behavior of dark matter itself independent of the galaxies inside of voids.
Which lensing sample is this? What shear sample is it?
It's from I supplied the voids. And
Are we looking to just in terms of the black line is the signal, the black point is the signal we're looking at?
yeah, black is the E mode signal. Red is the B mode signal, which we expect to be 0.
Yeah.
There should be no rotation. There is a model that predicts a very weak signal. So we're actually seeing a much stronger signal than you would expect from theoretical calculations.
But is there only that one point that's actually significantly from 0?
So there is this point that is, maybe a sigma away from 0. But the neighboring points are consistently below 0. Like there's a consistent dip in the profile. You can see here the error bars are here, 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 and this one. So what you have is a few neighboring points that aren't just scattering around 0 and then you have a big dip. You have a few consistent points that are turning away. And when you you evaluate the robustness of this, like how far away it is from 0, using whatever your favorite test is,
Yeah.
it's 1 or 2 sigma.
It looks like you've got an even more significant dip, the very large scale.
Yeah, this is interesting too. We're not exactly sure. But this is several factors larger than the void itself.
One of these sigma is the cumulative detection size of this
Yeah, 1 or 2 sigma.
Well, you've got 1 point that's 1 sigma, that's 2 sigma, right? But
This is one particular stack that I'm showing you. We have a bunch of different stacks from a bunch of different slices, and they all show this dip to varying strength.
But is one of the sigma fit to a 10 times more massive or more empty, more?
Yeah, I mean, I don't understand why our signal is so much stronger than the expected signal.
You usually see like the rest of the stack because you know, if your prior is kind of that your model is correct, then looking back and say, well, actually, I'm just going to take 5% hit to use the 2 sigma fluctuation.
Right. But it's what convinces us is that, but yeah, in the other stacks, we see a consistent dip. Some of them are less significant than others, but always at the void, or near the void radius, we see a dip. And each individual stack isn't necessarily significant in its measurement. You know, maybe less than 1 sigma, but when you add up 4 or 5 stacks, it all show this consistent signal. But yeah, we have no idea why it's so much larger.
The same with the ISW was the one segment. How many sigma?
Yeah, the sigma, the ISW2 is, you know, it's a 2-ish sigma measurement, which again is actually stronger than theoretical predictions. For this data set for the SDSS, you can calculate what the ISW effect should be, and it should be less than the level of noise. But it's not. We're seeing an ISW effect. And by rights recalculation.
but it's getting weaker as you add galaxies, eh?
As we're adding voids, so we start off with the largest voids.
I see.
So we're adding smaller and smaller voids, and you have to stretch the voids out and the CMB signal out. And so you start smearing things together, and it starts to get a little messy.
So it's not obvious that 936 voids is actually better than 231 voids.
Yeah. So this is this is of course incredibly preliminary and just very intriguing. I think we've decided the title is not going to be detection of the anti-aliasing probe, but something more like measurement of the. A little bit more cautious. And finally, we can use voids to look at magnetic fields, and Tim Arlen at UCLA is doing this. If you have a TeV blazon spitting out TeV photons, they can pass through a void, just traveling along, and they can pair produce into a positron and electron. If there is a weak magnetic field in the void, then the positrons and electrons, their paths will curve. And as they travel, they'll synchrotron in. So what you'll see is a high energy source surrounded by a relatively weak halo. But this is only true if there's a certain range of magnetic fields in the voids. If the magnetic field is 0 or too weak, then there's no curving of the path and there's no halo. If the magnetic field is too strong, greater than, say, 10 to the minus 12 Gauss, then the positrons and electrons will curve too quickly before they produce a halo. So if you're able to point, say, the Veritas instrument at a blazon, and you see a halo, and you know that there's a void between you and the emitter, you can put constraints on magnetic fields inside of voids. And if there's no way for magnetic fields to break out of clusters into the voids, then this tells you about primordial magnetic fields, which is a very interesting project, and Tim Arlen's working on this. So lastly, I want to talk about the project that we're most interested in, what motivated this analysis of voids in the first place. And this is the Alcock-Paczynski effect. So the Alcock-Paczynski effect tells you that if you have a set of standard spheres in the universe, you can do cosmology. You can take this population of spheres and measure their angular extent and their extent along the line of sight. If you take that ratio, a lot of things drop out, and you're left with something proportional to the angular diameter distance times the expansion rate at that ratio. So this gives you a probe of cosmology, because all of these are sensitive to cosmological parameters. All you need are a set of standard spheres. We can use clusters, except that the baryonic astrophysics in clusters and the peculiar motions of galaxies inside of clusters are 200 times stronger than this effect. So it washes out any of this Alcock-Paczynski effect inside of clusters. You can use the BAO, which you compare the correlation perpendicular to the line of sight to the correlation along the line of sight. This gives you an Alcock-Paczynski measurement. And in fact, this is the best and strongest use of Alcock-Paczynski measurement to date. Or you can use voids. But as we saw, voids are pretty messy. They're not spheres at all, and they have very irregular shapes. But when we stack many voids together, voids have no preferred direction in our universe. So if I stack enough voids together, I should get a sphere. In an isotropic universe, I should get a sphere. So here's the density profiles in light gray of individual voids. They're incredibly noisy. These are low density regions of the universe. But if I add many together, this qualitatively universal profile pops out. I get a qualitatively smooth-looking ellipse that I can perform the Alcock-Paczynski measurement.
How does redshift distortion affect the voids and the edges involved?
I'll talk about it. So Levaux and Wendell did this in simulations last year. Here's their one-dimensional profile in simulations, and here's a two-dimensional profile of the stacked void. So you see this underdense core, a very steep wall, and then a slightly overdense compensation region. And you can take this stacked ellipse, this stacked void, and fit an ellipse to it. And you can take the ratio, you can measure the width of the ellipse and the extent along the line of sight of that ellipse into cosmology. And here's what they found for various simulations. This is the expansion parameter, or the stretch along the line of sight as a function of redshift for various void stacks in simulations. And here's what you expect for a lambda CDM cosmology, for the cosmology that they put into the simulation. So you can essentially construct a Hubble diagram, but for the stretch of voids as a function of redshift. And they found that for a dense spectroscopic survey like Euclid, remember Euclid is designed to look for BAO, baryonic acoustic oscillation. You took the exact same instrument and instead used voids to do an Alcock-Paczynski test. Your constraints on dark energy equation of state parameters shrink by about a factor of 10. You know your uncertainties shrink by a factor of 10. And that's simply because of the statistical power in voids. A BAO signal is about 150 megaparsec. There's only so many 150 megaparsec patches in the sky. Your statistics are fundamentally limited. But voids are 5, 10, 20, 50 megaparsec across. That even though you have to sacrifice a lot of voids to form these stacks to get enough signal to measure their ellipticity, you have so many voids on the sky that you gain in statistical power.
How do you compare that between normal Alcock-Paczynski power factor within all galaxies? They are the same test.
Right. Statistically, I think it's compatible. But when you're doing Alcock-Paczynski with the power spectrum with all galaxies, you have to do a lot of modeling of the peculiar motions of galaxies. The peculiar motions of galaxies are stronger than the Alcock-Paczynski effect in the power spectrum. With voids, let me talk about that in just a little bit of the modeling you have to do with voids. to get extracted cosmologicals. So we're going to do this with the SDSS. Now the SDSS is not an ideal survey with voids. It's relatively sparse, doesn't go out to very high redshift. We can give it a shot, see if we get anything. Here are two-dimensional stacks from data, and you can see this underdense core, a sharp wall, slightly overdense region, the same kind of stacks that we saw in simulations. We can fit ellipses to it as a function of redshift, and we can get a measurement. Now here are the horizontal bars are the expected measurement for a lambda CDM cosmology. In colors, with the error bars, are individual stacks of various void sizes as a function of redshift. And then in black are the weighted average of all these independent measurements in that redshift bin. So the error bars are pretty big, right? Because this is a very sparse survey. It's hard to measure the ellipticities. It's not completely crazy. But interestingly, down here, in these thin gray lines, are the measurement that we expected from simulations. In simulations, peculiar velocities do impact the shapes of voids. They tend to squash voids along the line of sight. In fact, they tend to cancel out the Alcock-Paczynski effect. But Laveau and Rendell in their analysis found that I was a uniform 16% offset from the expected signal. It was very simple to model out. We didn't understand the source of it, but it was constant with redshift, and very uniform, just 16% offset. So they applied that correction and were able to get their cosmological results. But here, in the main sample of SDSS, we're not seeing the hints of the same sources of systematics. That's something we're trying to understand. When we apply it to DR9, this is very preliminary results. When we apply it to 3 redshift bins in DR9, we see a trend, which is key for the Alcock-Paczynski measurement, but we see it lining up more with the expected result from the simulation. This is something we don't really understand. And if we apply the same correction to the data that Laveau and Rendell applied to the simulation, that 16% correction for some sort of systematic due to fluid velocities, we can do likelihoods, and we get omega matter of 0.3 plus or minus 20%, which isn't bad for this first stab in the analysis. But we don't understand. Pure velocities do play a role. They do tend to change the shapes of voids. But it's on the level of 10 or 20%. And it's something that we need to understand through simulations and through analytical modeling. But we're on the case. It's something we're actively working on now. But even if the Alcock-Paczynski measurement turns out to not be robust with voids, we still have this publicly available void catalog where we can explore other interesting avenues of void research. Thank you.
Can you go back just 2 slides to your... So you've got in each redshift bin, so the redshift bins are different volumes, so they're probably independent, but you model the covariance between your different data points that within a redshift bin?
Within it, these are different stacks of voids. So this is, say, 20 to 30 megaparsec voids grouped together, 30 to 40 megaparsec voids. For this black error bar, we are just assuming they're completely independent.
I know nothing about it, but my intuition would tell me that they're not. That you have to model their covariance because they're in the same volume space, right?
True, but
these are overlapping structures. Your big voids all contain the small voids.
Actually, for the Alcock, I neglected to mention this. For the Alcock-Paczynski measurement, we only use independent voids. We don't use subvoids for this analysis. We only use top level. We can build a tree of voids that contain a subset of voids, and we only use the top level voids because of that issue.
But they still share like walls and stuff, right? So you might really be concerned that they. I mean, if you have you guys have mocks, right? There, so you I mean, you just have to perform this on your mocks, 100, well, 100 mocks. You do it.
Yeah, I mean,
100 times,
actually,
you do it
that's
right.
running. I started that running before I came to this one.
So the magnetic field TV halos, what kind of angular scale roughly would you expect? I imagine it depends on the strength of that magnetic field, and I don't know too much about having these satellites out there, but I think the resolution is not all that.
Actually, an instrument like Veritas, which is what Tim Harlan uses, has the resolution necessary to capture this, because there's, well, the halo is almost like an on-off state. Either there's going to be a wide halo that you can see with even a full resolution instrument, or there's going to be no halo at all. There aren't a lot of in-between cases because it really depends on the amount of voidness between us and the emitter and the strength of the magnetic fields in those voids. You either get a big halo or you get almost no halo at all.
I have one brief question. When you showed the void profile very earlier on, the smallest void thing, yeah. So there's the top left plot. There's obviously a distinct slope to the two, and the statistics look good enough. The profile of the
You mean this one?
yeah, well, and the blue versus the red.
Right.
So the others look they merge a lot, but the statistics are good enough that they're separate. Is there something I should be taking out of that?
The height of this compensation. Each of these different samples have slightly different densities, right? They're different volume limited samples. And so the steepness of the wall and the height of the compensation has something to do with the sampling density of the population. Right? So blue has a slightly lower density than red. So it will tend to have, just from Poisson statistics of the sampling itself, and also the biasing of the the tracers themselves, a slightly steeper wall and a slightly taller apparent compensation. What this means for the actual dark matter underdensity is something we're studying right now. And that's why we say qualitatively universal.
Right.
What's yours in the void counts if you were to have the sample? What's the impression drawn would affect the count for that event scatter, or would that give a systematic shift?
If you were to cut the sample in half, there would be, it would add scatter, yes, one. And two, you would tend to slightly tilt this, this number function because you would favor getting rid of larger voids rather than smaller ones. So you add more scatter and you slightly change the slope of the function.
And then the output efficiency, could any of the discrepancy between the main and the two mass samples be from the density? Like if you threw out 4 or 5 false galaxies for that?
Yeah, maybe. Yeah, it's something we're trying to understand with mocks and with simulations, and we're playing with the data. It's something we're trying to understand.
Great. Well, I think we'll wrap up now and go upstairs to cookies.